Hi, class. Today we're going to go over the final exam and how to solve each problem on it. So, for question number one here, we're asked to find the steady state expression for VO. And how you would do that is first you need to find the impedances of this inductor and this capacitor right here. So, if we do that, we can find that for the capacitor, the inductance is negative J20 ohms and the inductor is J60 ohms right here. So our next step would be to combine the impedances of the inductor and the resistor. These two are in parallel, so you use your parallel equation for inductance combination, which gets you 24 plus J12 ohms for these two. And that's going to be your ZX value, inductance X, when you're finding the steady state. And then your next step is to combine that with the inductance of the capacitor. And since they're in series, remember you combined these two already. So this inductance would be in series with this inductance, and then you just add them, and that gets you your equivalent inductance, which is 24 minus J8 ohms. So our final step would just be to plug that into the equation. We are given VG right here, which is 40 sine 50,000. To convert that to cosine, you just use a phase angle of negative 90 and make this cosine instead. And put that in the phasor domain, which is 40 angle negative 90. And multiply that by the ratio of Zx over Z equivalent, which gives you 30 plus J30 in rectangular form. So now we have to convert that over to polar form. Doing that would give you 42 angle 45 degrees, and then you just plug that back in to your cosine expression with the correct frequency, giving you a steady state expression of 42.3 cosine 50,000 T plus 45 degrees minus 90 degrees. And, you can simplify that to just negative 45 degrees. And that's all it is for question number one. Very easy. Next up is problem number two. This one is a little harder than question one, but it's still doable. I'll show you how. So your first step is to find the impedance of the capacitor right here. Doing so gives you negative J40 ohms, and then you would combine that impedance with the impedance of your resistor right here. They are in parallel, so you use your parallel equation and get 16 minus J8 ohms. Moving forward, what I would do next is find the impedance of the inductor right here, J18 ohms, and then do a source transformation, turn this current source into a voltage source. Doing so will put this parallel impedance that you would have here into series with the impedance of the inductor. That means you can just add them together and get an equivalent impedance of 16 plus J10 ohms. Next up, you're just going to turn that voltage source back into a current source, making your impedance along this side of the circuit in series with your 4 ohm resistor right here. So you can just add them again, getting a Thevenin equivalent impedance of 20 plus J10 ohms. Doing so also gives you the Thevenin equivalent voltage of 63.6 angle negative 32 degrees. Next up, we need to find the maximum average power, which, if you remember, is just the RMS voltage squared over 4 times the resistance. To find the RMS voltage, you just take that 63.6 from your Thevenin equivalent, divide it by root 2, and square it. Then you divide that by 4 times your resistance, which is 20. So 4 times 20 is 80. Divide that, and you get 25.3 watts. So, still pretty easy. That's your maximum average power, and all the steps along the way gave you the impedance L and the impedance Thevenin and the voltage Thevenin. So moving on to problem 3. This one is asking for the output current of this operational amplifier. So let's go and think about this real quick. We know that this current is going to be the same as this current through the 33 kilo ohm resistor because there's no current entering or exiting your op amp. So that means that the current through this resistor equals the current through this resistor equals the current through this resistor. So your next step is just to find what that current equals. We know that at a junction, the sum of current in equals the sum of current out. Or in other words, this current minus this current will give you this current, which is the same as your output current, as we just established. So to find the current through the first 10 kilo ohm resistor, you just need to do a transformation on your voltage source into a current source, which is pretty easy. Doing so gives you a current of 0.0025 angle 0. Next up, we need to find the current from this capacitor. The current of any capacitor is equal to the capacitance times the derivative of voltage. So you take the derivative of your voltage equation, which gives you negative 1.25 times 10 to the 6th sine 50,000 t. Now you multiply that by your capacitance, which is 200 times 10 to the 9th. And if you simplify that, you get negative 0.25 cosine 50,000 t minus 90 degrees. That's your phase angle, because remember, after you derive it, you're in sine. So to convert back over to cosine, you just use a phase angle of negative 90 degrees. Moving forward, we now know the current from the source and the current from the capacitor, so we can find the output current. Doing so gives you 0.25 cosine 50,000 t minus 89.4 degrees, which is very close to the current from the capacitor. Finally, we have problem number 4. For this problem, we are given two sources, and we have to find the steady state expression for the voltage right here. To do that, all we have to do is just use the law of superposition, which states that the voltage is equal to the voltage it experiences from this one plus the voltage it experiences from this source. So essentially, you just turn one off at a time, find the steady state expression through VO, which we already know how to do, and then add that with the other one. So step 1 would be to turn off VB and just pretend it's not even in the circuit. That would mean that you have this voltage source, an inductor in parallel with a resistor, and this capacitor up here. So since these two elements are in parallel, what you would do is find the impedance of the inductor and then use your parallel combination to find the equivalent impedance. So omega times 25 millihenries times J gives you J 400 ohms as the impedance. And then your ZX value is just that combined with the 400 ohm resistor. They're in parallel, so this gives you 200 plus J 200 ohms. And remember to save this value because we will need it when we find the steady state expression. Next up, you add it because it's in series with this capacitor, so you just find the impedance of this capacitor and add it straight to this impedance that would be right here. Doing so will give you, or finding the capacitor first. Sorry, I got ahead of myself. The impedance of the capacitor is negative J 100 ohms, and then adding that with the Zx value gives you an equivalent impedance of 200 plus J 100 ohms. Next up, we plug that into our equation for steady state voltage. VO equals VG times the ratio between Rx over R equivalent. So 10 angle 0, because remember we're using just this one, no phase angle. 10 angle 0 times 200 plus J200 over 200 plus J100 will give you a rectangular form of 12 plus J4 volts. Converting that to polar, we get 12.6 angle 18.4 volts, and putting that back into cosine form gives you 12.6 cosine 16,000 T plus 18.4 volts. So that is our steady state for just VA. Save this value, and now we will turn off VA, pretend it's not in the circuit, and focus on VB. As you can see, VB is upside down, so you may want to draw your picture accordingly. Either way, this inductor and this capacitor are now in series because VA is not in the circuit. So we do the same thing that we did in the other step. But remember that they have different impedances because there's different frequency for VB. That means we have to find the impedances all over again. Doing so will give you an impedance of J100 ohms for the inductor and negative J400 ohms for the capacitor. Combining them in series gives you J133.333333333 ohms. Next up, they're in series. These two, when you combine them, are in series with this 400 ohm resistance. So you can find the equivalent impedance, which is 400 plus J 133.33333 ohms. Next up, we just plug those values into the equation, and this in polar form is just going to be 20 angle 0 because there's no phase angle. So multiplying that by your ratio of Zx to Z equivalent will give you 6.32 angle 71.57 volts. Expressing that in your cosine form will give you 6.32 cosine 4000 T plus 71.6 degrees. Now, for the final steady state equation, you just add those two values. But remember, these are in different frequencies, so you cannot directly add them, meaning that your steady state expression is going to be 6.32 cosine 4000 T plus 71.6 degrees plus 12.6 cosine 16,000 T plus 18.4 degrees. And that's it. That's how you beat your final exam for AC circuits. Thank you very much.